There we go. All right. Got a new desk. Awesome. I got a new desk too. It's actually wood on top of sawhorses. That works. Oh, what is that a picture of on the desktop? That's Princeton University. So I visited my brother in Princeton September before last. So yeah, I needed new background, so there we go. I know, I was just noticing that. I'm not sure what the deal is. It's also weird because if you close it, there's like a circle in the middle. There we go. All right, let's see. Let's start with questions. So let's look at ODP 202 questions. We'll talk about 203, and then we'll start talking about PA1 some more. But any questions up front? All right. Well, let's do ODPs. I think working through my issues with 202 made 203 super easy. Excellent. Yeah, so these are supposed to build on each other, and in theory, right, the more of these ODPs you do, the easier they're going to get, right, until they're at the point where they really are, you know, perhaps a few minutes each. Right, struct node with 3 fields, data, next, and valid, right? And we're doing initialization here, so this is like the init function from PA1, but with different values. So, doesn't have to be more complex than this. Define a struct node, and you have to define that before you use it, right? And typically we define this outside of any function so that it's accessible everywhere in the file from that definition point on down. I used a type def in here just because I don't normally use type defs, and I wanted to, you know, have an example of that. So node is synonymous with uppercase node is synonymous with struct space node. And so my init function doesn't return anything, so I declare it as void. And the type is struct node star, or in this case, uppercase node star. This one line with 3 statements initializes element 0. So, you know, data, next, and valid set how they're supposed to. And then a for loop, and you can do this with a for loop, you can do a while loop, whatever, but you want to do this for elements 1, 2, 3, ... 97, 98, 99. So you want to do everything from 1 to 99 inclusive, okay? To me, a for loop makes that pretty straightforward to code because I initialize I to 1, and I run this loop as long as I is less than or equal to 99. And the increment happens at the bottom, so I don't have to think about that. And then inside the loop, element I, set the data, next, and valid fields accordingly. And that should assess fine. All right, so your next ODP 203 continues using struct nodes, but here you're going to implement your get node function. So if you remember from PA1, which we're going to talk a lot more about today, one of the required functions in there is an internal function called getNode. And so getNode is supposed to, let's see, so normally we wouldn't have data in the first node though yet. Yeah, so the first node, element 0, all we care about is the field called next. We don't do anything with the data field. Depending on how you write your code, you can choose to ignore the valid field, or you can set valid to 1 so that it doesn't accidentally get allocated. But data we pretty much ignore. But I'm going to suggest that you set the data value to something interesting so that, you know, if you accidentally stumble across the Sentinel node and think it's a data node, you'll see this recognizable number pop up in your linked list. And it'll be a tell saying, oh, I'm using the Sentinel node the wrong way. If you don't do that and the Sentinel happens to be initialized to 0, you get an extra 0 popping up in your list. Who knows where that's coming from? It could be that you hit the Sentinel, or it could be something totally unrelated. So it's nice to use magic values when you don't want to encounter them, right? To let you know if you've accidentally gone somewhere you shouldn't. So yeah, 404 or 42, or whatever, or dead beef in hex is always a good one if you're outputting in hex. It's just some negative number otherwise. Alright, so getNode should go through your array of struct nodes, find the first node where valid is 0, and return the index of that node. Okay, don't ever return the Sentinel node though. Right, so start looking at index 1, find the first node where valid is 0 and return that index. Alright, and then it says if there's no space available, if you look at elements 1 through 99 and valid is set in all of them, then you go ahead and you return my null. And that's your flag indicating that you're out of space. Alright, so that's exactly what your ODP203 is going to do. It's a get node. You're passing it an array of struct nodes. You can assume it has 100 elements in it. Assume element 0 is not supposed to be used, right? That's the Sentinel node. And look from elements 1 through 99. Return the first node where valid is 0. So it's the same setup as 202. There's no initialization taking place. Instead, you have a for loop from 1 to 99, and in that for loop, check to see if valid is 0. And if it is, then return that index. Now the other thing in let's see, do we do this in here? Yeah, the other difference in PA1 is that your getNode function for PA1, after you find a free spot, I want your getNode to set that valid field to 1. Okay, you don't have to do that for ODP203. It doesn't say you should do it. But for PA1, your getNode is exactly the same function as ODP203, except in addition to finding the first spot where valid is 0, and returning that index, you also set valid to 1. What we're doing here is a memory management piece, right? We're thinking of our memory as this array of struct nodes, and that valid flag of 0 tells us this memory is available. So when you need a chunk of memory to store a node in, you've got to find a chunk that's available. Well, that's what getNode does. It goes through and it finds a spot where the valid flag is 0, and it says, hey, here you go, here's a struct node you can use. But it sets the valid flag to 1 so that the next time you look for a free spot in memory, you don't get the same location, right? The valid flag of 1 says this is in use. And there's a counterpose to that, which is release node. And release node, you tell it the index of the node you want to release, and that thing just clears the valid flag. So it doesn't delete it in some real sense. Instead, what it does is it marks it as saying this node's available for someone else to use. Does that make sense? So 203, write a for loop, find the first spot where valid is 0, return the index. If you can't find that node, return a 0. Yeah, unless you overwrite your hard drive with zeros, which doesn't actually erase your hard drive. You have to write with an alternating pattern of 1s and 0s some number of times to make it sufficiently difficult for someone to figure out what was on your hard drive. You can Alright, so there's 203. And in here I said you can just return 0, right? In your PA1, your getNode function should return myNull. Okay? Even though myNull is 0, return myNull. Alright, we're going to go through some of these details of PA1 next. Alright. Does using myNull versus 0 save memory? No, it will save, using myNull versus 0 will save you time on PA2. Because PA1, we're basically doing a job that the operating system normally does for us. So PA2, we're going to use dynamic memory, so we're going to use malloc, and we're going to use free, and malloc will return a value of null when we run out of memory. Since we're writing our own version of malloc, which we're calling getNode, right? We want to compare the return value to myNull, which will be 0. That'll make sense when we get to PA2. And if you follow this and you stick to the myNull stuff, it'll make you smile when we get to PA2. Probably. Alright, so PA1 questions. I don't know how far people got on PA1. But I want to go through this. We were kind of at the end of class last time, and I got through enough that you could make a start over the weekend. But I want to go through this and cover the remaining pieces of this, including deliverables and the grading rubric. Alright, fair enough if you didn't get started yet. So linked list code. Let me show you a sample of what this looks like when you run it. So let me hop over here. So here's my sample main program. You run main and it prints out the prompt, right? And if I type something that it doesn't understand, it gives me this really brief help message to remind me of what the legal commands are. So insert a number, print the list of numbers, search for a number, delete a number, or exit the program. So if I say print, there's nothing in the list, so it just prints an empty line. Okay? And again, I want you to try to stick to exactly what the specification says your program should do. So for example, I'm not going to print this help message every time the user types a command. Because if they're typing commands and they're not making errors, they probably know what they're doing, and you're just kind of cluttering up the screen if you keep giving them lots of output, right? Your program is in service to the person running it. So do what they ask it to do, right? And don't do other stuff. So there's nothing in the list right now. If I search for something in the list, it's not going to find it. If I try to delete something from the list, it's not going to find it because the list is totally empty. So let's insert a number. Let's insert the number 20. And now if I print the list, there's a 20 in there. If I search for 20, it's found. If I search for 21, it's not found. If I delete 20, and then I print the list, it's empty again. And if I search for 20, it's not found. And if I try to delete 20 again, it's not found. So let's insert some numbers. Let's insert some prime numbers. So we'll put in a 13 and a 7 and a 3 and a 5 and an 11. And we'll put a 2 in there because we like 2 even though it's an even prime number. And now if I print my list, there's a sorted list of the numbers I just put in. Right? Now I'm not sorting when I say print. I'm sorting when I insert. Right, and that's important. Sorting a linked list is tricky. Sorting by inserting in the right spot is relatively easy compared to, doing a bubble sort or something on a linked list. And it's more efficient than taking an unsorted list and sorting it. All right, so now I can search for prime numbers. Is 6 prime? No. Is 11 prime? Yes, it is. Let's insert, 21. So there's a 21 at the end. That was a mistake. 21 shouldn't be in there because it's not prime. Let's delete it. Print the list. There's what's in the list. All right. That's all your program does. It lets you insert, print, search, delete. And I should be able to insert up to 99 things. If I try to insert a 100th thing, it will tell me that it's out of memory. If I try to insert something that's already in there, it should say node already in the list, and it should not appear twice. If you try to delete something twice, the second one won't succeed because it's not in the list after you delete it first. If I put it back in, it should go in the right spot, and so on. All right, so your main program is really just an exercise function to let you make calls to the guts of the assignment, which is this set of functions: init, add, print, delete, and search. And do your basic error checking if you try to insert something that's not a number, or delete something, or search for something, or you don't specify a number, right? And one good way to check this, right? Go ahead and search for a number, and then just type the number, the command S, and it should still recognize that as an error, right? If it doesn't, you're probably not using scanf right. But you can see, I've done a bunch of tests here, right? So all of this stuff. So to test your PA1, right, do more than just 2 or 3 tests. Just keep exercising it, try lots of different things, right? If you want, you could put all of these things in a script, and you could run PA1 less than this file that has all of these commands in it, right? Or you can just get really good at exercising your program. And you could write a script that tried to insert 100 things and see if it blows up. That's not bad. All right, and then I can use the X command to exit. All right, so that's what your code looks like when you run it. So let's go through here again and see what it says. Let's look at more details. So we've talked about the necessary functions, right? Initialize your array to hold an empty linked list. Add a number to the linked list. There is nothing in this description about what to do if the number is already in the list, right? So I don't care what you do. I don't care if you go ahead and you add it, or if you decide to ignore it, right? It says return 1 if successful, 0 if not successful. But you should never call this from your main program unless you've already confirmed the number's not in the list, because the main program says don't put a number in twice, right? Well, you can handle that inside main. Search for your number first. If it's in the list, don't call add. If it's not in the list, then go ahead and call add to put it in. Print will print out the elements from the list, and that's a really good first function to write. Because if you have a way to reliably print the contents of the list, you can use it for debugging. Right? As you're developing your add function, you can try adding a node and then call print. And then try adding another node and call print. So print's a good early function to develop. Delete, remove, search, searches for a number. And those are the implementation of the linked list as an abstract data type. These are the things that your main program is going to use to manipulate the list. But these functions themselves will use some other routines that you're going to write. And you can choose what routines you want to write, but I require you to use two in particular, get node and release node, which we talked about around ODP 203. So get node finds a spot in your array that you can use. Release node basically frees memory in your array by clearing a valid flag. All right, main program we just looked at. Let's talk about the pieces we didn't talk about on Friday. So deliverables. All of the above routines implemented as described. The main program as described that lets you test your functions. Lots of commenting specifically for each function. Describe its behavior, the inputs, the outputs, the expectations, the side effects, the possible errors, everything you can think of, function by function, right? So here's a function called getNode. What does it do? Gets a node. No, not good commenting. What does it do? It takes no arguments. It returns an integer. The return value is either the index of a free node or myNull if there's no space left. Side effects. What else does it do? It sets the valid flag to 1 in whatever node it returns the index of. Right? What's the purpose of this? This is used when we want to create a new node. We call getNode to find where we should put it in the array. Right? And if you get used to writing these comment blocks in the beginning of each function, especially if you come up with a standardized style for yourself for describing these things, it will help you in writing your code. So, there's this notion of top-down and bottom-up code development. A lot of what we do when we're writing C is bottom-up. We start with the lower-level functions and we build on top of them. Right? We can do top-down development. We can start by writing our main program as just a bunch of function calls. And then we can start developing those function calls as being, calls to other functions and so on. And, whether you go bottom up or top down is largely a personal choice, and usually it's a mix of them. I'm thinking about this when I'm describing it as fairly bottom up, right? So you make your getNode function, and you document it really well for yourself. And then, when you're trying to add a node and you need to find space in memory, you're just going to call getNode. Well, how do you call it? Well, there's no manual page for it, so you look in your source code and you find the little comment block in the top of the function. You say, oh yeah, so this will return myNull if it's empty. So now you add a check which says, if return value equals myNull, then do something. Yeah, top-down can seem weird, but it will start to feel really natural sometimes. Depending on how well thought. So I think the design has to be bottom up. You have to know what these lower level functions are. But there's something kind of satisfying to me about writing a main program that's, 5 lines of code, and that's it, I'm done. There's my main program. That's going to do everything, right? And it's only 5 lines of code. How cool is that? I'm going to go out and have a break now, And top-down works pretty well with objects sometimes. So 223, we may move to more of a top-down mindset. But yeah, find an approach that that resonates with you, and be open to having a change over time. All right, so plenty of commenting for each function. Put a comment block in there. explained in a set of comments appearing immediately before the function definition. Okay, so I want to see comment block, and then, you know, void integer get node parentheses blah blah blah, and then the definition of it. Okay, and then I still want comments in the code itself. The comment block says, what does this function do? What do I pass to it? What does it get back? What are the side effects? What can cause errors, etc. And then in the code, you know, when you have a for loop for I equals 1 to 99, what is that doing? Why are you going from 1 to 99? Put a comment there, either on the side of the for loop or right before it. Right? If you know, array bracket loop index dot valid equals 0 curly bracket, bunch of stuff happens and you exit. What is that stuff happening? Why is it happening there? Why do you care if this is equal to 0? Well, you care if it's equal to 0 because it means that block of memory is available. So let's mark it as in use and return its index. Put that in comments. Okay? Don't require yourself or me to reverse engineer your code to figure out what the purpose of it is. Okay? So lots of comments. I also want a comment block in the beginning of your main program with your name, the class name, the date, the assignment number, and in your own words, a description of what the program does. Not just linked list program, but, you know, enough so that if you handed this to somebody who is not taking this course, they would be able to tell you what this program does in detail. And you don't need, you know, ridiculous level of detail. You don't need to say, you know, if they insert an I followed by something that's not an integer, my scanf function will return a different number, right? That's stuff that goes down in the code. But for somebody looking at your main program, they should be able to tell what this does. Lets the user type in, you know, one-line commands to interact with a linked list. Options are, you know, inserting, searching, printing, deleting, or exiting the program. Something like that. All of which is relevant because of the grading. Okay, oh, let's finish this. I want a makefile. Okay, a good makefile, not just one that says GCC everything in the universe.c. Okay, but a nice tactical makefile like we were doing in 224, so that if I change one file in your repository and I say make, it only recompiles the things that need to change. Now, if you make all of this one big .c file, then it's just going to be, you know, GCC, that .c file. But I suggest breaking it into pieces, but that's not required. All right. This has to be in a GitLab repo named linked list, 2 uppercase L's, and that I have reporter access to. All right, grading rubric. If on the morning that I downloaded I cannot get to it, it's an automatic 20-point deduction. And I will put a note on Canvas. And you have 24 hours to correct the situation. If you forgot to add me as a reporter, if your second L in linked list was lowercase, 20-point deduction. Okay? These are simple things to check. So just double check, triple check, right? You're buying a house and this is the mortgage paperwork that you're trying to submit, and it's got to be submitted on time. Right? So just make sure that you're really careful with the submission. All right. If I cannot compile the code, if I can compile it but it's not runnable, something like that, that's a minimum 40-point deduction. Right. So we start from 60 out of 100 and go down from there. If you're not using mynull, that's going to cost you 10 points. So I really want you to use mynull instead of this magic number 0 anytime that you check for the next field to see if you're out of memory or if you're at the end of a list. Okay. If you're not doing the basic node structure, if you don't have a struct node defined and it doesn't have those 3 elements, you're not using an array of those, that's a 0. Okay. So coding a linked list in some totally different scheme that still works doesn't get you points. Okay. You got to be following the assignment. So those are sort of the coarse-grained requirements. The nittier, grittier requirements: proper makefile 10%, functioning get node function 10%, release node 10%, initialize and print 5% each, add, search, delete 10. Right. So these are your core functions. Total of 40% of your grade. Your main program is worth 10%. What do I mean by main program? it's got to work well. It's got to follow the requirements of the assignment. Yeah, go back to the 224 index. There are a number of references to makefiles, many of which we also go through examples of what the makefile is. And also around some of the programming assignments in 224, there's discussion of makefile requirements, especially towards the end. For ODP 203, how would you return the index? Just return parentheses, whatever variable the index name is in. So the function is defined to return an int. So int get node parentheses, etc. And then just return parentheses, whatever variable has your return value. Cool, yeah, homework 6 from 224, I think had a makefile. Alright, so main program 10%. The required commenting before each function, 5%. The commenting in the beginning of the main program with your name, class, date, assignment number, synopsis in your own words, 5%. Comments throughout the code, 5%. Proper indenting of code, 5%. By proper, I mean consistent, right? It means everything is indented and it's indented consistently. But, you know, do you indent the curly bracket or do you indent the stuff in the curly bracket? That's up to you. Okay, but I want consistency. So we're upping our game here, okay? Your commenting and indenting your coding style is now worth 15% of your grade. And you can expect this to hang or possibly rise, right? The makefile is worth 10%. So there's a quarter of your grade that has nothing to do with your code itself, right? And then the coding details are the other parts. There are places, there are schools and courses that do consider self-plagiarism. So it's not uncommon if you repeat a class that you'll be told you can't, you know, use code from the last time you took it. It's also not uncommon, you know, when you're taking a course that you can't turn in for a homework. You can't turn in a homework that includes things you turned in on previous homeworks. And that kind of makes sense, you know, like in a writing course, for example. If you took part of what you'd written and turned in before and used that to write something new, right, that could be considered, you know, kind of a cheat. For programming, it's a little different to me because, you know, programming is largely about reuse, and the reason for commenting and organizing and modularizing and learning about objects and all that is to encourage code reuse. So I don't usually you know, put limits on self-plagiarizing, right, on using your own stuff. Again, but be prepared because there are courses like at WSU where that is, you know, expressly forbidden, and you can lose points for it. So yeah, it's good to know ahead of time. All right. So any questions on any of this? All right, well, let's dig back into the guts of PA1. Let's start looking more at some pseudocode. And get into some specifics of how we're going to finish up PA1. So let me refresh. Let's suppose that our array of struct nodes is called list, because LL looks too much like 11. So we have an array of struct nodes called list. And so remember what this looks like. Good old array. Got data, next, valid. It's got 100 entries. And this first entry is super special. It's the Sentinel node. All right, we've done the init function, right? The init function should set, let me go pencil some of this. The init function should set valid here to be 1. It should set the next field to be my_null. And it should set all of these valids to be 0. Alright, that's our initialized list. And let's suppose there's some data in our list. So let's just imagine our list has 2, 3, 5, 7. Let's put 4 primes into it. So this might be what our list looks like. All right. This is an example. A more interesting example than a purely trivial example, but an example of what your array of struct nodes might look like corresponding to this linked list, 2, 3, 5, 7. Right? Now, how do I know that this is what's in the list, assuming I didn't make more mistakes than you already saw? We start with element 0, that's the Sentinel node. The next field tells us where the first node of the list is. That's index 4. That's containing the number 2. That's this number right here. The next field tells us where the next node is, which is index 5. At index 5, we find element 3. And the next field tells us where the next node in the list is, which it says is at index 2. And at index 2, we find the number 5. And that node's next field tells us where the next node is in the list, which says it's at index 1, and at index 1 we find the number 7. And that node's next field tells us where the next node in the list is, but it says the next node is at location my_null, which is our flag saying that's the end of the list. So this array contains the list 2, 3, 5, 7. And this is, the way the array might look if I had done, insert 2, insert 5, insert 6, delete 6, insert 3, insert 7, delete 7, insert 7. Right? If I'd done a bunch of inserts and deletes, and right now, this is what my list looks like, the data in my array is going to be all jumbled up, right? And my array bounces from here to here to here, back up to here, and back up to there. Okay? That's going to happen the more you run your code. So instead of, storing a 2 and a 3 and a 5 and a 7 consecutively in the first 4 locations, when I'm thinking about the code, I like to start with an array that's kind of more interesting, that's sort of jumbled up. So I don't accidentally do something like, always start with element 1 or something like that. So that one little detail there can save you, days of debugging time, right? Don't make things easy on yourself. Right? Jumble up your data in your sample array that you're going to think about while you're sketching out this code. Alright, so scrambled data is always helpful. So let's look at our print function. Okay, like I said, print is a good early function to develop because once it's working, you can use it to help develop your other functions. So our print function just takes a pointer to the array of struct nodes and prints out the contents of the linked list. Alright, so to avoid print, it takes a array. I'm just going to call it list in here also, but it doesn't have to be the same name as that. But I feel like using the word list today. Alright, so first thing we want to do is print the first node in the linked list. How do we find the first node in the linked list? Somebody give me a description or a snippet of code or something. How do we find the first node in the linked list? Look at where the sentinel node is pointing. That's exactly right. So where is the sentinel node? The sentinel node is always at index 0. Right? The sentinel node is list bracket 0. So when I say node, I mean an entry in this array. And since this is an array of struct nodes, when I say node, I mean a struct node. I mean something that has a data, a next, and a valid field. So list bracket 0 is a node, meaning it's a struct node, meaning it has a data, a next, and a valid field. Well, I don't really care about the valid field of this because I know the sentinel's always there. I definitely don't care about the data field of this, but I very much care about the next field. So in chat, when someone said, look where the sentinel node is pointing, how do we know where it's pointing? It's list bracket 0 dot next. Okay, that is an integer, which is the index of the first node. So let me do something like this. I'm going to make an integer called current. And I'm going to say current equals list bracket 0 dot next. Which means when I first execute the statement, it's going to look at list bracket 0 dot next. Current is going to be equal to 4. Alright, what's the meaning of 4? 4 is the index where I find a struct node, which is the first node of the list. So I'd like to print out that node's data value. So I want to print list bracket current dot data. Everybody okay with that? Since current is the index of the first node, if I look at list bracket current dot data, that's the data value of the first node. So I want to print that. Alright, here's the magic. Given that current is the index of my first node, how do I find the index of the second node? The node that comes after current. And we've got it in chat. List bracket current is the first node of the list. It's a struct node. A struct node has a field called next, which is the index of the following node. So list bracket current dot next, that's the index of the second node. And we can double check. Current is 4, list bracket 4 dot next is a 5. Hey, 5 is the index of that next node, the node containing a 3. In my mind, as I'm coding this, I'm thinking I'm going to have this temporary variable called current, and current is always going to be the node that I want to print out. So in pictures, I've got my nodes. Current's going to point me to the node I want to print. So to move down the list, I'm going to change the value of current to be each node in succession. So I'm going to do something like this. Current equals list bracket current dot next. Well, once I do this, current is this 3 node. How do I print its data value? Print list bracket current dot data. How do I move to the node after that? Current equals list bracket current dot next. That'll move me to here. How do I print that node's data? Print list bracket current dot data. How do I move down? Current equals list current dot next. We've got a loop here, right? So down here, just want to go back to my print. Alright, this is heavy. Make peace with this somehow, or try to make peace with it. Right? Think about what's happening here. This is printing a data value. This is moving to the next node in the list. Go back, print the data value, move to the next node in the list. This is traversing the list. And this is what we're going to do when we search, when we delete, when we print, when we free up the list in PA2, when we do anything with our data structures, right? Typically we have some way of traversing or moving through all the stuff in our data structure. Alright, there's one detail missing here. What stops this loop from being an infinite loop? Because if we just, put this in a do forever loop, it's just going to keep running and running and running. So how do we know when it's done? That's where my null comes in, right? What happens when current is this 7 node? We come back up here, print list bracket current dot data. Well, current is going to be equal to 1, right, which is the index of the 7 node. So we'll print list bracket 1 dot data, that prints the 7. And then we set current equal to list current dot next. Well, list current dot next is my null. So our loop ends when after doing this, current is equal to my null. So let's just write that. And now we've got our loop in there, but after current gets a new value, if it's equal to my null, it will exit the loop. And bonus, what happens if your list is empty to begin with? Well, your sentinel node has a next value of my null. So when I initialize current to sentinel's next, current will be my null, and the first time I try to go through this loop, it'll exit immediately. So this code not only works for an arbitrary linked list, it works for an empty linked list as well. And when you find that happening, that's a really good feeling. That gives you confidence that you're following a good path here. All right, So think about this when you want to write code to work with this, right? I suggest just initializing an array by hand, right? Make an array of struct nodes and, data bracket 0 dot next equals this, valid equals this, data 1 data equals this, dot next equals that, and so on. Just write some code to build yourself a list piece by piece. It takes some typing, you can get better at VI while you're doing this, and then, using that list, you can exercise your other functions. All right, so we'll talk about that tomorrow, and we'll go through the same kind of approach to doing insertion and deletion, and search is pretty straightforward. All right, cool. I will see you next time. Thanks.